Attendees are in listen-only
Good
mode.
afternoon, everybody, and welcome to today's webinar. My name is Cheryl Jennison DeProsa, and I'm joined here at Shure HQ by Gino Sigismondi, as per usual. And we are joined by Sam Drazen, who is a user experience designer here at Shure. And they're going to talk us all through frequency coordination for wireless systems, a very important topic with lots of things to learn. But before we get into that, just a few items of housekeeping. This webinar will be recorded, as they always are. So if you go to shure.com/training and click on Webinar Archives, this will be up probably early next week. We also keep all of our past webinars there, so if there's a topic you're interested in, search there and you might be able to find it. We've got a lot of great, useful information there. So shure.com/training. Second item of note, if we're going through the process today and you have any questions, please feel free to type those in the question pane in the right-hand side of your screen. If you can't see that little question pane, you might see a little toolbar with an orange box with a white arrow. Just click on that. That will maximize the question pane and you can enter in any questions you have. We will be holding on questions until the end of the webinar and we will get to as many as possible. But if we don't get to your question or if it's a little bit of a deeper thing, you can always send your questions to support@shure.com and one of our applications engineers will be happy to answer you. So without further ado, we're going to dive in right now. Take it away, Gino and Sam.
Okay, thanks, Cheryl, and thanks, Sam, for joining me here today.
Thank you for having me.
And thanks to everyone for coming in and listening to our webinar on frequency coordination today. If any of you were on last month's webinar on antenna selection and placement and remote mounting and all of that good stuff, this webinar this month is kind of really part 2 of the series, if you want to think of it that way, because those two things really go hand in hand. In other words, both need to be paid attention to if you expect to have a wireless microphone system that is going to operate as you would like it to. And as with last month's topic as well, I mean, this is stuff that applies really when we're talking about larger systems with a lot more channels on the air. Getting one wireless microphone system to work, there's usually not too much trick to it. 2, not too much more difficult. As soon as you start getting to 3 or more, all of these things like frequency coordination and antenna placement start to become more and more important. And the more systems you're trying to run, the more important all of these things become. So whenever we get calls into the support team here looking for help troubleshooting wireless microphone systems, it really always comes down to one of these two areas. Either there's something not correct in the antenna setup, or the frequencies have not been coordinated properly. If both of those things are paid attention to with the appropriate care and detail, then chances are your system is gonna work pretty well. It always comes down to these two areas. So if you weren't able to be on the webinar last month, that topic is currently archived at shure.com/training. So after we finish up today, I encourage you to go back and take a look at that one so you get the complete picture of best practices for setting up your wireless audio systems. So I thought it would be a good to kind of start with a little definition of what frequency compatibility is, and it's the act of coordinating your wireless system frequencies to minimize the effects of system-to-system interference and outside interference. The outside interference is kind of intuitive. I think people generally get the concept, right? There are other things, radio things out there in the world that could interfere with your wireless microphone system. So of course you have to be cognizant of those things, but you also have to be aware of the fact that your wireless microphone systems or in-ear monitor systems, whatever wireless audio systems you happen to be using, can interact with each other and produce additional interference products that are related to the frequencies you're actually using. And if you don't pay attention to these things, then it can be difficult to get your systems to work properly. So really it's a two-pronged thing we need to be looking at here to make sure that your systems operate properly. So to that end, we're going to talk about system-to-system interference, what it is, why it's there, and what you need to keep in mind to avoid it, as well as avoiding outside television, broadcast television interference, which is the primary source of outside interference that you're going to have to deal with UHF wireless microphone systems. And then we'll tie it all together by looking at how you actually practically coordinate frequencies. Generally, it requires some sort of a software program. We'll demonstrate it using Shure's Wireless Workbench 6 software, which is a pretty powerful and free tool for being able to do this. And that's what Sam is here to tell us all about. He's the expert in Wireless Workbench 6, and there are other tools you can use it, but of course this is our example. So that's what we're going to do here. Before I get into some definitions here, I thought we'd actually run a little poll first, some audience participation time. I want to, just for our benefit, I guess more than anybody else, but I suppose everybody else on the webinar, we want to see who we're dealing with. So if you could just input for us by answering a question on the poll, the approximate number of channels that you usually are coordinating for your wireless microphone systems. We'll let it run for 30, 45 seconds here and see what we come up with. You know, the rules are the same, really, no matter how many channels you are coordinating for. That doesn't really make any sort of a difference there. So you know, you have to follow the same basic guidelines, but as we'll see, particularly when we talk about Wireless Workbench, there's different levers that you might need to pull, or different tricks you need to pull out of your magic hat sometimes to get those larger number of systems working. So looks like we're kind of stalling out here around 82%, so I'm going to call it. Some great voter turnout, by the way. So let's stop it. All right. So let's see what we got here. We have, wow, look at that, 49%, almost 50% in the 10 to 20 range. So a little bit different demographic than we had for our earlier session this morning, where it was more people in the less than 10 category. But 10 to 20 is a pretty good number of wireless systems. So good. Well, that helps us give an idea of who's listening today. So we will use that information and go forward. So starting on the basic end of things, just to make sure that we kind of getting everybody on the same page here, let's start with a few basic concepts that we want to keep in the back of our minds as we go through this. Kind of an obvious one, but usually worth stating. Whenever you're using more than one wireless microphone system, they all have to be on separate frequencies. If you have two transmitters transmitting on the same frequency, chaos will ensue, meaning that your wireless mics aren't going to work the way you want them to. So of course they all need to be different from each other, and actually spaced apart by a certain amount as well. And not only do they need to be different frequencies, but you have to go through a logical, conscious act of coordinating them so that they work well with one another. Frequency coordination is not a random process. It's not good enough that they're different. It's not good enough that they're just far apart. You know, oh, I spaced them, you know, far enough apart. That should be good, right? None of that matters. There has to be a conscious effort put into the act of coming up with this list of frequencies to make sure that they are the best possible list for where you happen to be using them. And the where is important because we're also trying to avoid interference from local digital television broadcast. That's actual over-the-air broadcast television, not analog terrestrial over the air. So it's not satellite, it's not cable, certainly not Netflix. These are the actual old-fashioned TV signals that you'd pick up with an antenna on your roof. We need to know what those are, and to find out what they are, we need to know where you are specifically. That's your location is a specific bullet point to successful wireless frequency operation. And then it's really important to know the total number of channels that you're planning on using. And that includes existing systems. That doesn't mean just, what you might be buying today or what you're thinking of buying tomorrow, but how many systems do you already have, and what frequencies are those operating on, and what's the manufacturer. All of that information becomes important in characterizing these systems and in picking frequencies that will all work well together. And again, the reason this webinar is entitled frequency coordination for wireless audio systems is because in-ear monitor systems and comm systems, those things are all important. They all operate in the same spectrum. So any device that's operating in the UHF television band needs to be part of your overall coordination plan. So first of all, let's talk about system-to-system interference. These are the interactions that occur, or that could occur, when multiple transmitters and receivers really are operating in the same location. There are a number of different interactions that could possibly occur, but the two that we're concerned about, because they're the ones that are most likely to be an issue, are minimum frequency separation and transmitter intermodulation distortion products. Dealing first with minimum frequency separation. Of course, as I said earlier, every frequency needs to be unique and you can't have two transmitters on the same frequency, but they also need to be spaced some distance apart. In other words, there's such a thing as being too close together. Unfortunately, there's not one number that applies no matter which wireless microphone systems you happen to be using. The distance that frequencies need to be separated depends largely on the filtering in the receiver itself, or what's called the selectivity of the receiver. And it can range, the spacing can range from as little as 400 kilohertz, or in the case of some higher end systems, even slightly less than that, up to as much as 1.5 megahertz apart for a more, let's say, more affordable wireless microphone system. And of course, the further apart the frequencies are from each other, that then I should say, the greater the required minimum spacing, that's going to further reduce the total number of systems that you might be able to get on the air. And that's one of the kind of main things that separates sort of an entry level system from a high end system, is the number of channels you can get on the air, which again is largely based on this receiver selectivity. If you were to try and sort of plot out what this filter might look like, just like any kind of filter, whether it's an audio or a radio, there's some sort of slope associated with the filter. It's not infinitely narrow just on the frequency that you would like it to be tuned to. So that's kind of what we're looking at here. This kind of bell curve represents the slope of a filter on actually a pretty decent wireless receiver with pretty good filtering. So what this means is that if you have a transmitter at, say, 600 megahertz with a receiver tuned to has its filter tuned to 600 megahertz, it would obviously pick up that transmitter no problem. But if we were to fire up another transmitter at 600.2 megahertz, the receiver would also be perfectly happy to pick up that transmitter, because it's really only, the receiver's filtering is really only 3 dB less sensitive, 200 kilohertz off from its main frequency. So you probably wouldn't want your second transmitter to be tuned to that close in frequency. But if you go up to 400 kilohertz apart, so 600.4 in this case, then it's perfectly fine, because now you're at that filter. It's like it's 50 dB down point. That's far enough down that it's really not going to cause any issues with this receiver if you have another transmitter at that frequency. Now, again, this would be on a pretty good system. On another system, this bell might be a much fatter bell, which means your keep out window is much wider. And again, that's going to vary per manufacturer. Now, do you need to know this information? Do you need to have this in your brain? Do you need to research exactly what the minimum frequency specifications are for every wireless you plan to use? Well, no, this is one of the things that the software can take into account for you. It might be useful, depending on what kind of user you are, to know this, but it's not critical that you know these numbers.
That's an important takeaway to remember too. We're going to get even deeper into the intermodulation spacing and stuff like that. All of these things are critical, all of them matter, and effectively none of them you need to carry around in your pocket necessarily if you've got the right tools that can take all this into consideration. So don't go running for the hills just yet. There's
We're going to show you why there's a lot of scary math, and then we're going to show you the tool that hides all the scary math from you.
Now you see it, now you don't.
So now talking about intermodulation, primarily in wireless microphone systems, we're mainly concerned with the intermodulation that can occur, the products that are produced when multiple transmitters are operating in relatively close proximity to one another. So if we look at the spectrum analyzer screen capture on the left here, we're looking at a 6 megahertz window. Only the two peaks labeled with numbers 1 and 2 are actual transmitters, wireless mic transmitters that are on the air. The other peaks that you see, which of course are frequencies that you would need to avoid, are intermodulation products that are created by these two transmitters when they get close enough to essentially pick each other up. So one transmitter's output, the frequency generated by this transmitter, I should say, mixes with the output of the output stage of this other transmitter, and they produce additional frequencies, and vice versa. So the strength of these intermods is actually directly proportional to the proximity of the transmitters. So the closer the transmitters get, the stronger these products become. The further apart they get, the weaker they become. But they are there. And, you sometimes think of them as like phantom products, because if we weren't looking at them on a spectrum analyzer there, you wouldn't necessarily know that they were there. But I think this illustrates, again, why you can't randomly select frequencies and just say, well, they're far enough apart, because you could look at these two and say, well, these are all, these frequencies are 2 megahertz apart. That's great. I'll just space all of my frequencies 2 megahertz apart, and then they should be far enough apart. Except in that case, if you did that, every system you were using would be landing on intermod frequencies, which would be, you'd be interfering with itself in the worst possible case scenario here.
Another thing worth mentioning is that not only are the intermod products a factor of how close the transmitters are to one another when they're transmitting, there's also a factor of how high the output power is of these transmitters. The higher the output power, the stronger the intermod products will be, the more trouble you would be in if one of your receivers happened to tune to one of those frequencies where an intermod was being placed. So again, I guess another thing that is worth mentioning is that in general, you really want to be operating on the lowest transmit power that you possibly can to get the necessary coverage for your transmit to receive distance. And that's just to be a polite RF neighbor, but also to reduce your chances for spurious intermod products messing up your reception.
Yeah, the more channels you're using, the better off you are to keep your transmit power low. And just like in the antenna webinar last month, where we said don't keep adding more gain to your antenna system because it can cause more problems. Same thing here in RF. More power is not necessarily the solution. Now, if you're just using one wireless mic and you're trying to get 1,000 feet of range on a golf course, have at it. Crank it up. The FCC allows licensed users up to 250 milliwatts if your hardware can get there. But for multi-system applications, lower is generally better. Now, on some newer systems, kind of like what's shown on the right here with our ULX Digital, you'll notice that the intermods are barely noticeable, if at all. And that's not just because it's digital. That's part of what plays into it, but part of it is also just advancements in transmitter design. As transmitters get more linear, then the intermod products get noticeably weaker. So in this case, it's not that there aren't any intermods being generated by these two ULXD transmitters, but it's that their level is so low, they're essentially buried in the noise floor, which is good, because that means that those are frequencies you can reuse more easily, and it would allow you to get more systems on the air. So all wireless mic systems are not created equal in terms of how much or how many intermods are produced, or at least produced in a way that is harmful. So again, this is a function of the nonlinearity of wireless mic transmitters. Again, a linear circuit is something where when two signals are combined in a linear circuit, what comes out is just those two original signals. But in a nonlinear circuit, and again, all wireless mic transmitters are nonlinear to a certain extent, you get these additional intermod products. To just take a quick look at what the math is, for those of you who are brave. It's actually pretty easy math for one system. If we have a transmitter at 590 megahertz and we turn on another one at 595 megahertz, that's far enough apart. They're perfectly happy and they're not interfering with each other. But remember, these two transmitters are interacting and producing additional frequencies at 585 and 600 megahertz. And there could even be more products than that. These are just what are called the third order intermodulation products, and they're typically the strongest. There could be fifth order, seventh order, ninth order. I mean, depending on the system we're looking at, maybe you have to consider those, but on most higher end systems, you don't. But at any rate, that's the third order intermod products. So that means that we wouldn't want to add a third wireless mic system on either one of those frequencies. Again, how do we know what those frequencies are? These are all perfectly predictable using math. There's the formulas if you are curious, but that's how we're able to predict these things. So if we wanted to pick a third frequency to go along with these, we need to make sure that we not only stay far enough away from our original two frequencies, we need to stay away from those intermods first. So we could pick 603 megahertz, and that would be fine. We now have transmitters at 590, 595, and 603 megahertz. Those work well together. But all three of those transmitters interact to produce three transmitter intermodulation products. And there you can see the math associated with those. It's a slightly different formula, but still mathematically predictable. However, that's not it, because each pair of transmitters, so these first two, and numbers 2 and 3, and numbers 1 and 3, are also producing two transmitter intermod between each pair there. And so that ends up looking something like this. Again, our 3 transmitters, these work totally fine together, but by just having 3 transmitters on the air, there is 9 additional frequencies that need to be avoided in order to make sure that this system is going to work properly. And again, these are all mathematically predictable. We can know where those frequencies are. We have software programs that do such a thing, so we'd be able to pick our 4th frequency successfully. If you tried to do it randomly just by guessing and saying, well, I don't know, how about 611, that seems far enough away. Well, no, you'd be landing right on an intermod product here, so maybe that wouldn't be the best choice.
Seems like a lot to keep track of.
Kind of is. Yeah. I mean, if you were to have to do this without some help from some other devices, you'd have a lot to keep track of in your brain. So and just to further beat the point home, this screen capture from a Win Radio scanner just shows 9 wireless mic transmitters illustrated or highlighted in red, so you can see which ones those are. Everything else here is an intermod product. So trying to pick a 10th frequency at random, it's just not gonna happen. You don't necessarily need to dive into software right off the bat. Most manufacturers have put some smarts into the receivers, the hardware themselves, to help you figure these things out. Any tunable wireless mic system usually has some pre-programmed sets of compatible frequencies in them. So these are sets that we've already vetted, calculated for you, that we know are compatible, and we call them groups. So within any given receiver, you may have a set number of groups and a certain number of channels within that group. The key then to making sure that all of your wireless microphones work together well are to set them all to the same group and different channels within that group. If you mix and match groups, all bets are off. And again, we get this question a lot when someone calls in for troubleshooting help, but they have a pile of wireless that isn't working, and we ask them to start by telling us what groups and channels they're using, and it's, well, we have group 1 channel 2 and group 3 channel 9 and group 6 channel 6 and groups. It's like, wait, stop right there. The first thing you do to try and fix that is put everybody back to the same group and different channels within that group. Now, there's a couple of caveats on that. This really only applies if all of the systems you're using are the same model, say all ULXD, because that's what's pictured here, and in the same frequency band. So for any given tunable wireless microphone system, there typically are different frequency bands you could buy that tune in different sections or slices of the UHF spectrum. So if you're using ULXDs and they're in the J50 band, as long as they're all J50, this works. If it's a mix of some J50 and some H50, groups and channels don't mean anything anymore, and that's where you need to start looking into a tool like Wireless Workbench for frequency coordination. But all the same system in the same band, use the groups and channels, totally works.
Now, would this work, Gino, if I wanted to add like 5 of these systems to an existing set of wireless gear already that might be a different brand or a different model?
Well, no, because then you have to consider the frequencies that those things are tuned to or can tune to, and those will impact the frequencies you choose here. So again, you'd need to come back to an overall plan using something like Wireless Workbench.
So groups and channels seem like they're ideal for operating that set of wireless in kind of isolation, really, just when that's the only thing.
If that's the only thing you're using.
Part of the mix. Okay, cool.
Right, exactly. But the second part of it, even if you've paid attention to everything we've talked about so far, is making sure that you're avoiding outside interference from digital television channels. And we'll show you how you can find out what those are. One way I suppose, would be if you actually have an antenna hooked up to your TV, is you could just tune through the TV stations and see what are on the air. But that's kind of a poor man's scanning device, isn't it? But it would work. Actually, not poor. TVs aren't cheap. But anyway, that's what you really need to worry about is television channels that are within about a 50-mile radius of your location. Sometimes you can cheat on that a little bit if you're indoors, because the building structure usually provides some shielding, which means that some of the signals from more distant TV transmitters may not penetrate, and those frequencies would be cleared inside the venue. So it's some subtle tweaks you can make when you're looking at these things. But a really important point is that the TV channels that are being used by broadcast television change from city to city. So in other words, what what DTV channels are on the air, the frequencies they use in Chicago are not the same frequencies that are used for broadcast in Detroit or in Cleveland or in New York City or wherever you happen to be. So in a touring application, it's really important to look at this on a daily basis. Whenever you move to a new location, you can't just assume like, well, what I used last night in Chicago should work fine in Detroit. That's not the case. You really need to redo your frequency plan based on the local RF conditions and what TV channels are on the air. So that said, there's a couple of different ways you can figure out what TV channels are on the air. You can always go to the web for finding out this information. The Shure website has a frequency finder where you can enter your location and it will tell you for a specific wireless system, like again, in this case, ULXD, here's the groups and channels that we recommend for the J50 frequency band. You can choose by frequency band and see what's available. Or if you scroll further down the page, actually see literally what TV channels are on the air and the actual call letters and the channel number and the distance that you are from the actual transmitters and all of these sorts of things. So there's some good information there.
This solution is great, the frequency finder, especially if you want to check out how many systems you could purchase or you could install of one particular model of device. But one thing that this tool can't do, and what we'll get more into in the software in a second, is taking more than one system into consideration. If you needed in-ear monitors and microphone systems, this tool doesn't have the flexibility to help you. But it's great for just a very quick survey of, we need this many channels of this type of system. How many can we fit in this city in Oklahoma?
Right.
You know?
And getting back to the frequency band issue again here too. So all of these 4 frequency bands that are available for ULXD, these numbers you see here are shown in isolation. That means you can use up to 14 J50s or 5 H50s or 27 G50s or 14 L50s, but you can't use 14 J50s plus 5 H50s plus 27 G50s plus 14 L50s.
That's a
You'd
good
have to go
distinction.
into Workbench to coordinate those.
Gino, is this tool built for the United States only, or is it for other countries as well?
Yeah, the one on the Shure America's website is for the U.S. only. That's a great point. And the reason for that being is that we recently updated the frequency finder to pull officially sanctioned FCC information from the white spaces database providers. These are the source of truth for what TV channels are actually on the air and what space is available for wireless microphones. So if you're in Canada or Mexico or other parts of the Americas, this tool unfortunately doesn't help you because it's reliant on FCC data only. But that's something that another way Workbench can help you, because it does include television information from many other countries. So that would be worth looking at. But on the website, this is where you can find that information. There are other places as well. There's FCC Info is one. TV Fool is another one. There are several good resources out there for trying to figure out what TV channels are on the air. And if you're outside of the United States, your local telecommunications regulatory agency should be able to help you or point you in the direction where you might be able to find that information. Or you could do what we really like to encourage people to do, which is find a way to scan the radio spectrum in your area. You can consult databases all you want, but a database is just information about what should be on the air, what's probably on the air, what's authorized to be on the air. But a scanning device will do a scan and tell you exactly what is on the air. And scanning can take a couple of different forms. In the case of scanning built into some of our products or receivers, that's just the receiver going and looking for what frequencies that it can tune to that are actually clear. It will scan and identify the best frequency for you. But things like a full-blown spectrum analyzer or even some of these little handheld guys that you can get out there now will actually graphically show you what signals are on the air and how strong those signals are and what specific frequencies they're at. And you can use that information to try and come up with and find out what frequencies are clear and make it more of a manual process. But again, a lot of our products are able to scan and find a clear frequency for you.
Quick question, Gino. What is that handheld scanner there in the middle? Someone was asking.
The manufacturer of that is TTI, capital T, lowercase I.
There's a number of popular portable handheld scanners. Some others people might have heard of include RF Explorer. Coleman Creations makes a number of products too. I mean, there's a bunch out there.
The Win Radio ones are devices that hook up to your computer via USB and allow you to run software on your computer. to talk to the radio over USB and capture scan data that way.
Yeah. But the point I think that Gino was making, and I think is really good to call out, is that there are really two types of scans. There's the site survey scan that really tunes to every frequency and visualizes the spectrum in front of you. And I think there's a number of things that come from that. One, confidence of what's in the spectrum, and two, you can enable software products to avoid noisy spectrum. And then the other type of scanning, which I think we'll get to in the next slide, is the ability for I know a lot of Shure products have this capability to scan through just the tunable frequencies that a particular device can tune to and listen in on each one of those frequencies and pick the one that has the lowest noise level. And so here's a brief video of a ULXD receiver scanning through group 1, finding the first compatible frequency that's clean and without noise, and then tuning the receiver to that frequency. So this is a great utility that a lot of our wireless products have to help you get up and running without the need for a software suite and connecting everything together via the network. If you had one wireless system, it seems like this would be a great way to get it up and running very quickly.
And again, if all of your wireless systems are the same system, again, all ULXD in the same frequency band, maybe it's again, J50 or whatever, then you can, so there's two parts, right? There's, again, coming back to making sure you avoid system to system interference by keeping everything tuned to same groups and different channels within that group. And then using the scan function to make sure that the receiver picks channels within that group that are clear. So you really can't do one without the other. Always set everything to the same group in different channels, but then make sure you're taking advantage of scanning if the receiver has it, to know which channels to use. If you have an older system that doesn't have any scanning capability, that's where then you maybe need to consult the website and find out what channels we recommend based on the database information. But if you have a scan feature, that should always be your go-to, because that always knows better than a database what frequencies are actually clear in your area. So again, kind of sum up what we just said here: use groups and channels and do scanning if everything is in the same frequency band. If it's not, which in a lot of cases it's not, that's when you have to get into a programming, or I should say calculating a custom compatible set of frequencies by observing minimum channel to channel spacing, avoiding intermods, and that's, I should say, avoiding landing on intermods. That's a point I like to make, is that when you use software to calculate frequencies, it doesn't get rid of or eliminate intermods. They're always there, but a calculated compatible set of frequencies avoids landing on intermods that would interfere with your system. That's a very important distinction there. And again, you always want to make sure you're avoiding outside interference. And so this is usually done with a computer program, because as you saw, the math just for getting 3 systems on the air is quite a bit. So you can imagine doing 20 or 30 with pen and paper, it would get a little hairy. So that's why we have computer programs that can handle this sort of thing for you. So there are a number of tools that can be employed for this. Of course, we're going to show you demonstrate using Shure Wireless Workbench version 6. The AXT600 is Spectrum Manager, is a scanning radio from Shure that is a dedicated scanner that actually has onboard frequency coordination, very similar to what can be done with Workbench 6. Again, the Win Radio and TTI scanners, RF Explorer, these are all things we mentioned earlier. Professional Wireless Systems makes another intermod software that can also be used for coordination. But I think we want to take a look at what we can do here with Wireless Workbench for these purposes.
So the demo that we're going to show you today, I think we're going to run through 2 use cases. The first one is going to be a simplified demonstration of what somebody who would be running wireless in, let's say, a house of worship or a small venue could do right now, today, for free, to get themselves a list of compatible frequencies that in almost every scenario is going to be better than arbitrarily picking frequencies. And then in the second demo, we'll step it up a bit, show a coordination with a few more frequencies. We'll incorporate some scan data and see how you can use the tools in Wireless Workbench 6 to get a compatible frequency in a very treacherous RF environment. So the first thing I want to do is paint a picture for you here. Let's say you are tasked to put 10 channels of wireless in a house of worship, or the house of worship already has 10 channels of wireless, but no one's ever coordinated it, and who knows how the wireless got there, but you need to make the best performance possible out of that gear. What Wireless Workbench can do is allow you to specify this inventory of devices that you have, and then based on the types of devices that you've added, it can find compatible frequencies for each type of device. Wireless Workbench comes with a library of devices, the whole collection of Shure devices that operate wirelessly that we make. And also it comes pre-configured with wireless devices from a number of other manufacturers that you can add. This just lets you get the most comprehensive set of information possible about the equipment you're using. And I think that's really the moral of the story. The more information you can give, the better the coordination is going to be. And that comes true in every part of the application. So let's do something really simple. We've got SLX in the G5 band, let's say. The church has owned it for a long time, and they've got 8 channels. So what I'll do is I will add this gear to my inventory, and you'll see the little channels pop up here. Now, SLX is not a networked wireless system. Wireless Workbench can't control and interact those systems over the network, but we can at least virtualize those devices and use the presence of these things here to find good frequencies. So if we jump into the frequency coordination tab, we've got a lot of tools at our disposal here, but there's a really straightforward workflow to follow through here, and it's really all around this right sidebar here. So if you do nothing else, knowing to follow through these steps will get you to where you need to go to get a good coordination. So the first thing I'll do is I will select the frequencies from the inventory and just pull everything in there into this calculator. So this calculator is sort of its own little application unto itself. So I just pulled my 8 channels of SLX here into the frequency coordination tab. And these aren't network devices, and let's assume that I can't acquire any scan data, which we mentioned earlier is definitely the best way to characterize your RF environment. We still, however, want to make sure that we can know roughly the RF stuff that's going on where we're going to be operating. So what we'll do is, since we don't have scan data, we'll jump down to the TV channels dialog, and we'll click this gear to open up this dialog. And this lets us search by our location for any nearby TV transmitters. So we're in the United States, and let's say this church is right down the street from Shure headquarters in the lovely city of Niles. So I'll enter in our postal code and press search, and I can adjust the radius of search, let's say 35 miles here. And when I search, what this is doing is going into the database that Workbench has, and it knows the location of a lot of these high-power TV transmitters. So the result of this search includes a number of transmitters, including those with regard to public safety. Public safety channels aren't always relevant in every city in the United States, but we've got a few of them, and we've got 2 in Chicago. So if you scroll down this list, you'll see by call sign and by frequency, all of the TV stations that are within our radius, our specified radius, that we ought to avoid. And this is just a good way to get up and running without having a scan or any other detailed information about knowing where we probably shouldn't operate frequencies. So when I press save, you'll notice that all the checked channels then become these red bars. And these red bars are ways to inform the calculator to not put frequencies there because those are the places where TV transmitters could be transmitting. So with that, we really don't need to do much else other than calculate frequencies. We've added our frequencies into this view. We've given our postal code to render out a list of TV channels to avoid. And when we press calculate, what you'll see happen is the calculator will come up with a set of 8 frequencies. And that was so fast, we almost probably missed it. Let me zoom in here so we can get a better view of the action. And I can calculate a number of different solutions. Each one might look a little bit different. But you'll see that the frequency markers in this plot view get distributed in a way such that none of the TV channels we aim to avoid are being overlapped by the frequencies. And the frequency placements themselves are all compatible with one another. So this achieves 2 things. One, inter-system compatibility. The frequencies, while they might look random, are mathematically sound not to create intermod products on top of one another. And 2, to the best of our ability, we've avoided RF interference from the outside world, TV channels being the primary source that we're able to take care of. Now, if you could get a scan in Wireless Workbench, either from a networked Shure device or a scan file from our forum or from our applications FAQ page or from a buddy who's got a spectrum manager, all of that would be even better because you've got a much more accurate view of the spectrum where you might be operating. And you could, pick frequencies more appropriately. But if nothing else, what we've just done right now is sufficient to get frequencies that are compatible with one another up for your gear to go. So,
and you noted that they are different every time you hit calculate. And I had gotten a question actually from a customer last week. They just called because they were confused because every time they calculated, it was a different set of numbers. And I think the expectation was, well, shouldn't it be the same every time? Am I doing something wrong?
That's a great question. Wireless Workbench has a pretty advanced algorithm in its engine that finds compatible frequencies. And what it does, you can think of it like playing Yahtzee, I suppose. Frequencies are, and it's funny, but it's true. Frequencies are scattered in the spectrum in a number of iterative cycles to find the ideal placement of frequencies, both quickly and compatibly. And I won't go too much more into the details of how the algorithm works, but the point is that there are many solutions that will render, potentially a very, very good scenario. And it would be computationally not really worth it to go through every permutation of frequencies for every device, especially with large systems, to get the one single best solution. But for these 8 channels, no problem. We found a solution very quickly. So how do we?
It is very fast, and I think that's kind of the important takeaway from this. I hope is that for people who haven't used Workbench before, it may, coordinating frequencies may sound like a big scary thing, but for a small number of systems like this, it's literally just tell the computer program what you have in your inventory, tell it your zip code, and hit calculate.
Yeah, and computers are built to do math, and that's all it's doing. A bunch of small, algorithmic computations very quickly. It doesn't need to be painful. Honestly, the most painful thing for non-networked Shure devices or non-networked devices at all is getting the devices to their frequencies, which is really the next step. Once you've got these frequencies calculated, you can generate a report with this little button here. And what this report is great for is handing out to your A2 or a technician or yourself, going and then assigning each one of these frequencies for which the group and channel and frequency values provided to all the systems here. And this is where you can actually implement then that coordination that Workbench has given to you. So this is pretty straightforward. Again, since the app is free, you could download this now and try this at home. This is already way better than just turning wireless on and hoping for the best. But let's turn it up one more level now. I'm going to open a show file that I've prepared in advance to show you what a little bit more of an chaotic or treacherous RF environment looks like. So you can see how wireless Workbench can help navigate those waters as well. Because this is what really, the more channels you get, the more essential a situation like this would become, where there's just too much wireless to coordinate by hand. I don't even know why you would try. So I've got an inventory here populated with a number of things. I've got some wireless microphone systems from Shure and from other manufacturers. In addition, I've got some in-ear monitor systems and some intercoms. So we really try to take as broad a scope of view, of the wireless that might be on a particular backline for a touring thing or whatever. And in our inventory view, I've got all this stuff pulled in, and you can see it looks like RF Armageddon over here, So I'm going to hide some things so we can call out each piece of the view. The first thing I want to mention is this is what scan data looks like in the application. And the reason it's significant is because it's not just a pretty picture. The scan that's been captured is actually being processed by the application. In addition, with this red line, this exclusion threshold, to generate these blue bars. And these blue bars signify exclusions, or where frequencies shall not be put. Now, this is really important because with scan data that has been captured, ideally with the same antennas of your wireless rig and the same venue where you're going to be operating wireless, we now are instantly avoiding any spectrum that surpasses our RF noise threshold for pain effectively. And you've got full flexibility to move this line up and down depending on your need for more spectrum to use or your need for cleaner spectrum to use. So the flexibility is really in the user's hands to tailor this thing here, but it's extremely quick to get data up and to get exclusions up and running to avoid noisy spectrum. So thanks to a friend, this data came from the MGM in Las Vegas. Wouldn't want to be running wireless there myself, but it's got to happen all the time. So if I collapse this view, you see we've got a number of wireless channels here, from things like the Telex intercoms to PSM 1000, UH-Far and Axient, and even some Sennheiser channels. And all of these systems now, because they're all in one application, we can let the calculator do its thing and do all the math for us under one roof. And we know that frequencies both for Shure and non-Shure devices will be compatible with one another thanks to the calculator. So as I calculate these frequencies, you'll see it strain a bit, and that's good. We set it up so that we wouldn't find all the frequencies we asked for at first. To give you some tips and show some features of the application that let you relax the criteria for compatibility in some appropriate ways. Because not all shows are candy canes and lollipops when it comes to finding frequencies. So you can think of frequencies. Let me expand these again so we can look at these a little bit more. So each of these sets of frequencies, I'll collapse it again, has basically an idea of its own personal space. Actually, you know what I'll do? I'll open the dialog that shows us how to define these things. So for every type of device that wireless workbench can coordinate frequencies for, there's some data under the hood. And this data under the hood, you can see it in the equipment profiles dialog. It defines what kind of space each one of these systems needs in the spectrum. A really linear system that Gino was describing that might have newer components and might be more of a robust RF performer might need less personal space than a relatively older system with older components or cheaper components that might need more personal space in the spectrum. And by personal space, what that really translates to are these numbers here that define the filtering and intermod considerations taken for each system. And in effect, we've got 3 profiles for each one of our systems, each one of the bands of our systems and all systems that define how much space is needed. And these numbers correspond to larger numbers equal more personal space equals less simultaneous channels on the air. So for all these systems, including these competitive ones, we've got profiles built for these that come with wireless workbench. In addition, if you're using wireless systems that we don't provide, you can build your own. And if I wanted to, I could either create a brand new one from scratch here, or I could select a particular, if I wanted to branch off or Gino made his own. Let's see, if Gino wanted to make Gino's awesome wireless. What I could do is I could copy the parameters from that telex system I selected, and now I've got all that data in terms of where it tunes and how it tunes copied in here, and I can tweak these parameters accordingly to correspond with whatever wireless system that you might be using. And the manufacturer of the wireless system in question can probably provide a lot of this information. But the point is, this data specifies how much space each one of these frequencies needs. Now, I want to call out these profiles again because for each given system, we have the choice to relax our standards for how much personal space a particular frequency needs. And why that's relevant is, okay, we're in the situation where we're not getting all the frequencies we need. What are we going to do? One thing we can do is start to loosen the requirements for some of our frequencies by changing frequencies for each one of our types of devices to more frequencies. That's just a more aggressive compatibility profile. And when we calculate frequencies again, you'll notice we find everything we've asked for. So this is because we've sort of lessened the spacing requirements for all these channels.
And you could do the opposite if you were in a more ideal situation and make it more robust if you wanted to, correct?
That's a great question, Cheryl. Yeah, absolutely you could. So let's say some of our frequencies, let's say for our Axion system, are corresponding to a VIP talent or mission critical channels that need as much space as possible. You can totally change those things, and we found it anyways there, such that the channels that need the most robust performance get the most robust frequencies. And that flexibility is built right in there. That's just one of the tools you've got to adjust how your frequencies are compatibly found. This exclusion threshold is also another control too to really very directly impact what spectrum is usable and what spectrum is not usable. I'll turn these markers back on here too. But looking at these markers, you can tell the math here is non-trivial, and it's not something that you'd want to 40 minutes before the show with like a coffee stained Post-it note try to jot down on pencil and paper to find a solution. It wouldn't be that wouldn't be good stuff to do. I'll show off Wireless Workbench 6.11, which is the version we're looking at right now. It's actually not released yet, but it'll be available by the end of April 2015. There's some really cool features you can do. You can tell Wireless Workbench is a very mathematical approach. This frequency here looks like it just is compatible, but it's very close to some energy right here, this scan peak here. You can actually move markers around in Wireless Workbench 6.11 and then reanalyze things to see if they're compatible. That one's obviously not compatible now because he's red, but I could move them around in a variety of different locations so that you can coordinate frequencies visually as well using that human element of expertise. The program is a great tool to do a lot of the heavy lifting, but at the end of the day, the human's got to make the final call to make sure things are going smoothly. So that's just a little glance at frequency coordination, the tools that are available. And the one thing I want to call out before we depart from this view is that when it comes to Shure networked wireless gear, particularly some of the newer stuff, this becomes so much more convenient because instead of generating a report now that someone's got to go manually tune receivers and transmitters to the specific frequencies, users can assign and deploy directly all of their frequencies, their coordinated frequencies, straight to the gear. So that step of tuning devices to the proper frequency is now a push of a button, and their assignments can even be tweaked manually if they wanted to. But it's that simple. So that's a little bit of a glimpse of frequency coordination, how it can be alleviated by the application.
Great. Thank you very much. As you mentioned, this is version 6.11, which we are still looking for to be released later this month. So if you went and downloaded it today, what you would see would look a little bit different than what we just saw, but it's coming very soon. And a lot of the functionality is still there. It just looks different. And just a couple of general tips. I know we didn't spend a lot of time looking at the mega applications of lots and lots and lots of wireless. But again, the more wireless you're using and the more crowded the RF environment is, the more important it is to try and capture that scan data. I think we've kind of beat that point home. But a couple other things that often get overlooked is using band planning to keep your different types of devices in different parts of the spectrum. So if you have wireless mics and wireless in-ears and wireless comms all on the same show, try to keep those in different parts of the UHF spectrum. Don't get your wireless mics and your wireless ears all mixed up in the same frequency band, especially because wireless in-ears operate at often much higher power levels too, which can affect performance. And sometimes you don't get to choose. Sometimes you get stuck with what you're stuck with. And there's a great feature in Workbench that's called inclusions, that even if you do have wireless mics and in-ears that are in similar tuning ranges, you can use the inclusions feature to force the program to put your ears in a different part of that band than your mics go, so they're not kind of intermingled. So that's a great thing. And then lastly, there's the concept of RF zones, which is if you are, you could use the MGM Grand as an example. There's often multiple venues using wireless within that theater. And if you can do an overall coordination for the casino where you take each room or each venue within the overall structure as a separate zone, then that'll often allow you to get more channels on the air. So zoning is another good way to often get that channel count increased. Again, and the reason that works is because we come back to the concept of intermodulation again and how those products are created. And remember, it's largely based on how physically close the transmitters are to one another. So a venue at one end of the casino where there's a transmitter there is not going to create an intermod with a transmitter that's being used in another venue on the other side of the casino, right? You probably still want to avoid duplicating frequencies, but you don't have to calculate intermods across venues like that.
The help system in Wireless Workbench actually has got a great article on zones if you wanted more information. That's a great resource to read a little bit more about how they're used.
And there's videos on the forum too, correct?
Yeah.
Great. Okay, so that said, before we get into the Q&A, I just want to plug our next webinar, May 18th. We're going to get away from wireless for a change here and talk about wired mics and how to choose them. It'll be a great primer on microphone basics and how that all kind of comes into play when you're selecting a microphone. It's a topic that, believe it or not, we get asked that question quite a bit. What's the best microphone, or what's the best microphone for me? We'll help you.
Good question.
Good question. And you can always visit shure.com/training for more updates on when registration will be available for that. And with that, we have a few minutes left if there's any questions out there.
Okay, we have a lot of questions. I don't know if we're going to get to all of them today. So if we don't get to your question, please send an email to support@shure.com. We have a great team of applications engineers that monitor that email address and can get back to you with whatever questions you have. So please feel free to utilize that. And I pre-apologize if I miss your question. Just send it to them. They'll take care of it. So let's start here. Let's see. I'm just trying to weed through what the best one is here to start with. Question about Wireless Workbench 6.11. Is there RF Explorer compatibility?
Wireless Workbench 6, even previous versions of 6.11, have the capability of importing scan files taken from a number of third-party devices. I believe that RF Explorer files will be imported if they're exported in a CSV format. You just need to strip any spurious header information out and just give Wireless Workbench the raw data. There's an article in the help system that tells you exactly the format that you need that scan data to be in. But the takeaway is has to be in CSV, and if it's formatted just with frequency and dBm level, it should be fine.
And keep in mind that means Workbench has no hooks in it to directly control that device.
That's
it's
correct.
Just a matter of importing scan data that can be captured by devices like an RF Explorer or a Win Radio or something like
That's a
that.
good clarification. Yeah.
So sort of on that note, are there any specific devices that measure and put that information directly into Wireless Workbench?
The only devices that Workbench 6 can actually control and capture data from in a live fashion are Shure networked devices. So all of our receivers, the PSM 1000 receiver included, and the Axient Spectrum Manager.
Okay. What is the lowest cost Shure system that has the assign and deploy features?
The lowest, all of our network systems would fall into that category, and the lowest cost one of all of them would be QLXD. That's our newest digital wireless system.
Okay. Can intermodulation happen between one system and an external TV broadcast frequency?
That's an interesting question.
It was more likely to happen with analog television, where you have to kind of look at these on a spectrum analyzer to get a better idea of the difference. But analog television, even though it occupied a 6 megahertz channel, it was actually 3 discrete carriers sort of within that channel, and you could actually have intermod occur between that one of those peaks in the analog signal and a wireless microphone. It didn't happen a lot, but it could happen. But a digital signal is a much different character because its energy is sort of spread or distributed across that entire 6 megahertz chunk of spectrum. So it's less likely that that distributed energy is going to form an intermod product with a discrete wireless microphone signal.
So especially in today's day and age in the United States, chances are no, considering how much we've switched to DTV. But it's worth looking at if you can get your eyes on an image, maybe Google or something, of what a DTV versus an analog TV transmission looks like, and that might make a little bit more sense.
Okay, great. Well, unfortunately, we have a lot of questions here, but it looks like we are just about out of time. So please, like I said, send those questions into support@shure.com, and we will get back to you. Just want to thank you so much for joining us today, and hopefully we will see you next time.